So this video introduces two new terms, alpha being algebraic over a field and transcendental over a field. So we say alpha is algebraic over a field f if there's some polynomial with coefficients in your field that has alpha as a root or a zero. If that's not possible, then alpha is transcendental. So let's see some examples. Here are some algebraic numbers over the rationals. So I could do 2, square root of 2, I, and even 2 minus I. These are all algebraic over the rationals because I could find polynomials with rational coefficients that have these as roots. For instance, x minus 2, x squared minus 2, x squared plus 1. And I think for the last number, I can choose x squared minus 4x plus 5. 2 is a root of the first polynomial, the square root of 2 is the root of the second, I is a root of the third, and 2 minus I is a root of the fourth polynomial. So these are all algebraic over Q. Here are some transcendental numbers. Transcendental over the rationals again. So pi happens to be transcendental over the rationals. There's no way you could find a polynomial with rational coefficients that has pi as a root. It's actually kind of difficult to prove this, so I'm not going to even attempt it in this video. It's a challenging problem. It took many years for people to find the proof of this fact, but indeed it is transcendental. Similarly, e is a transcendental number over the rationals. There's no polynomial with e as a root that has rational coefficients. I think I'll end my examples of transcendental numbers with one more transcendental number. Actually, the first number that was ever proven to be transcendental is this one. So you can have a decimal expansion which begins with 1 and then continues with 1, 1, 0, 0, 0, 1, 0, 0, and I'm going to put a bunch of zeros and a 1, a bunch of zeros and a 1. And the positions of the ones are in the decimal places that correspond to the factorial numbers. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, so I'll put a 1 in position 6. 4 factorial is 24, so I placed the decimal digit 1 in the 24th position here. And then 5 factorial would be the position of the next one, and 6 factorial the next one. So the ones get more and more spread out as you go along. That was actually the first number that was ever proven to be transcendental. The proof of this fact relies on not much more than the mean value theorem from calculus, but it's not worth going into the details of the proof. So here are examples of transcendental numbers. Now, if you hand me a random complex number, like pi plus e, I will not be able to tell you if it is indeed transcendental. It is very difficult to prove that a number is indeed transcendental. However, the number of algebraic numbers over Q is countable, a countably infinite set. So there are an uncountable number of transcendental numbers over the rationals, meaning there are many, many, many more transcendental numbers over the rationals than there are algebraic, but still very difficult to completely prove that any given example is indeed transcendental. So let's state and prove a theorem about algebraic and transcendental numbers. So here's the main theorem about them. So theorem. So let alpha be an element in E, which I am going to tell you is an extension field of F. So alpha is in here, and I'm going to let phi denote the evaluation homomorphism that's going to take polynomials with coefficients in your field and give you back elements in your extension field. And I'm going to define the evaluation homomorphism so that any polynomial p is sent to p of alpha. So we've seen this example before. It's a ring homomorphism. Then I'm going to say two facts about this. Number one, alpha is transcendental if and only if this evaluation homomorphism is one-to-one. What that means is that I have a one-to-one ring homomorphism from the polynomials with coefficients in my field to E, meaning that E contains a subring isomorphic to this polynomial ring. And then the second condition I'd like to write down and prove is that if alpha is algebraic, then there is a unique monic, irreducible polynomial p of x with coefficients in your field such that p of alpha is 0, and furthermore, if f of alpha equals 0 for some polynomial with coefficients in your field, then p of x divides f of x. So in some sense, I'm saying that there exists a unique minimum irreducible polynomial, like the smallest one, so that if you have any other polynomial that has alpha as a root, then your smaller polynomial has to divide that f. So let's prove this fact. So I guess I have two statements here. The first one is a pretty easy proof. So being transcendental is the exact same condition as the kernel of this evaluation homomorphism being just the zero polynomial. The evaluation homomorphism evaluates your polynomial at alpha, and if it's transcendental, the result can never ever be 0. That's the definition of transcendental. You'll never get it to be the 0 of any polynomial. So the only way that you can get out 0 in this evaluation homomorphism is if you started with the 0 polynomial to begin with. Now, a kernel of a homomorphism being just 0 is the exact same logical condition as this function being one-to-one. So that's the proof of the first statement. Now, the second statement follows from the fact that the kernel of the evaluation homomorphism is an ideal. So the kernel is generated by a single polynomial because the kernel is an ideal in the polynomial ring over a field. And we've proved that polynomials, the polynomial rings, are principal ideal domains, which mean exactly this statement. Principal ideal domains mean any ideal is generated by a single element in that ring. So there we go. We have this, and I might as well say that my polynomial is monic. Monic just means the coefficient of the highest power of x, the leading term is 1. If this polynomial is not monic, you can just divide by the leading coefficient, since we're in a field, and make it monic. So I have a monic polynomial. I also know that it's in the kernel. P of x is in the kernel, meaning if I evaluate p at alpha, I get 0. So here, let's see what I've proved so far. I have monic polynomial that has this condition. So let me next prove that p of x divides any other polynomial f that satisfies alpha being a root. So if f of alpha is 0, then that's the same condition as f of x being in the kernel, and the kernel is generated by this monic polynomial, and what this ideal means is that f of x is p of x times something else. So p divides f. So now I've proved this condition. So what remains to be shown is that this polynomial p is the unique monic polynomial and also irreducible. So let's say p of x is generates an ideal that's also equal to some other q of x. So maybe there's another polynomial q, maybe monic polynomial, that generates the same ideal as p. I'm trying to prove this uniqueness property. Well, then alpha is a root of q and p, so what we just showed is that p would have to divide q, and reversing the logic, q divides p, and since they're monic polynomials, the leading coefficients are the same, p of x equals q of x. So there's the uniqueness property. And I think the final last detail we need to verify is the irreducibility criterion. So if p of x is a product of two other polynomials, like a of x times b of x, then if I evaluate at alpha, 0 is equal to a of alpha times b of alpha, or alpha, meaning that either a of alpha equals 0 or b of alpha equals 0. These are two elements in a field, E, and a field is an integral domain after all. So one of these has to be 0. So if, let's say, a of alpha is 0, then a of alpha, actually a of x, is in the ideal generated by p of x, meaning the degree of a has to be at least that of p. So the degree of a is bigger than or equal to the degree of p, but the only way that can happen, since p is a times b, is if the degree of a is actually equal to the degree of p, in which case b has to be a unit. Then b is a unit, just an element in my field, meaning that I can't have a non-trivial factorization of p. This shows that p is indeed irreducible. And if b of alpha is 0, a symmetric argument holds. So this proves that I indeed have an irreducible p. Okay, great. I'll see you next time.